All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you all had a good weekend. I know that this course is like, we have to do work on the weekend. I know that, I'm sorry. I still hope that you had a chance to take a break, a little bit of a break. I hope they had a chance to catch up on some sleep, hang out with people, watch TV, do something fun. If you can see, kind of blurry in the background here, I went out to Narcissus with my son, and this is a photo that he took with me. He took for me. I'm just going to open it right up because I'm proud of my son. I'm proud of my son for taking this photo. It's really nice. This is that's the kind of snake that you find at Narcissus. And those are my hands. Like, so it's not like mega-sized anaconda sort of thing like it is on the screen here. They're really small. They're really the worst thing that happens. I'm sorry. I'll close it. I'll close the window. I'm sorry. The worst thing that happens with these snakes is that this one pooped on my hands. Yeah, they don't bite. They're harmless. They're nervous. Like, you can calm them down a little bit by holding them in your hands. I'm going to stop talking about snakes just in case it's making you feel uncomfortable. It's supposed to be better next weekend, though. So if you do find the time, next weekend might be a good time to go. In terms of where we are in the course, first and foremost, just like double checking here, I am recording right now. Where we are in the course, last Friday, I posted like kind of a summary video. Got some positive feedback about that, so thank you for the positive feedback. I'm just going to keep doing that. There's only 5 times that I need to do this still, and it's not really a big effort for me to do it, so I'm more than happy to do that at the end every week to make sure that we're on the same spot. With that in mind, so lab 1 was due on Friday. Assignment 1 is now due this Friday. Next week is a really short week for us. Monday's a holiday. Friday has a class scheduled in Aurora, but I am canceling that class. That class is canceled, so please don't come here on Friday if you don't need to be here on Friday for this class. And then we have a midterm test on Thursday, which is just like, I am kind of reeling at how fast we're getting to that, but it's going to be on Thursday. And so what I want to do on Thursday of this week is talk about the test. So I know we're impatient to find out more about it, but please just be patient until Thursday, and then we'll talk about the test. That's also part of the reason for canceling the class on Friday. Why would you want to come here immediately after you just wrote a test to learn something new? So let's just take a break. I think that's it in terms of announcements that I want to make. Are there any questions about anything before we get into material for today? Oh, the lab grades were back already. Kyle is fast. He did it over the weekend. They are back. They are in your inbox in Learn right now. Okay, cool. All right, so this week our topic is threads. However, we still have one thing that we need to finish from last week, and that's primarily what we're going to focus on today. So last week we were working on IPC, interprocess communication, and the outcomes that you have been seeing for the last couple of classes are write code where processes communicate through message passing via signals, pipes, and FIFOs. We have written some code and we have demonstrated the use of signals. So register a signal handler. We can send signals to those processes either using a program on the command line, or we can send it with an API call, which is kill. We've got this idea of pipes. So we can create these queues that live in the operating system space that are shared between processes that are related to each other By inheritance, I'm going to use that word inheritance. I don't mean inheritance in the 2150 sense. I mean it in the sense of like there's a parent and a child process. One of them duplicates itself, and we've got this shared queue that's between them, and they can use this to communicate with each other. And then today what we're going to look at is FIFOs. In the discussion of FIFOs today, we're also going to be talking about that whole like through the lens of synchronization through the lens of through the lens of synchronization, that outcome. I just didn't want to put it here because it would make this 10 times too long, but we're also going to be thinking about that and talking about that as we're looking at FIFOs today. The other thing that I want us to be able to do probably by the end of today's lecture, and kind of in the context of the reading that you're doing for this week, is to begin to be able to compare and contrast processes, threads, and applications. Applications here, I'm going to give you a synonym for this in terms of what I have been saying. This is program, so this like inert file on disk. When I'm saying the word application here, or when it's described as application on the learning outcomes document on the CS page, it's program. That's the synonym here. Processes and threads, I'm using the exact same terminology to describe those things. So those I don't need to provide synonyms for. But I want us to be able to start making comparisons between what it is that we're doing with processes. So things like the mechanical use of APIs for working with these types of concurrent things. So fork and exec and wait versus pthread create, pthread join. Communication between these concurrency mechanisms. So piping for inter-process communication, signals for inter-process communication, and then being able to just change variables in threads. Threads are sharing the same address space, processes are not sharing the same address space, so comparing the way that we have to communicate between those things. Applications in here, I'm going to say this doesn't really fit into the course material in terms of the way that we've organized things, but like compare and contrast processes, threads, and applications. Applications / programs is like inert file on disk. Processes and threads are concurrency mechanisms. They're tools for running things. So one of them is kind of like it's a file, and the other one is like running code. That's kind of the main way that you can compare those two things. I am mostly interested in compare and contrast between processes and threads. That's what I am mostly interested in, is compare and contrast between processes and threads, and a lot less about that third part there. All right, so I want to take a look at Lab 1. I've said this before, and I'll say it again. The labs are designed, they are intentionally designed to lead up to the assignment. The stuff that you're doing in the lab is intended to basically be a mini stepping stone to what you're going to be doing in the assignment. I am going to focus on the octopipe part. The binary file thing it's interesting. Like there's one thing that I found to be tricky when I was doing it myself, which was like reading that location to find an offset and then going to that location, just this kind of weird indirection thing. But once you get to that point, then going through the rest of it is straightforward, and it kind of just like copy paste of what I was doing in class, and that's fine. The other part of like stepping stone from Lab 1 to assignment 1 for that is the bonus part. So I'm less inclined to go through that part because it's just a bonus in the assignment. I want to really focus on the octopipe part, the pipe, fork, dupe to, and wait. So I forgot to put wait in there, but I do mean wait. So like making sure that we're waiting for processes to finish after they have completed. I'm going to show you code. I'm going to show you my solution. I am not going to post my solution to the course webpage as a file. It will be streamed on YouTube. The video will be there, but I'm not publishing the file itself. So you can see the source code in the video, but I'm not going to give you the file to just copy and paste stuff from. All right, so let me go back from my, my proud father moment here to Lab 1, guide octopipe. And I've got a file here called octopipe.c. I could run this, but it's kind of going to look like what you've seen already with Octopipe. The one thing that you may not have seen, I guess, if you didn't look at the forum, is that one of them is this cat. I like this cat example, cat, 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 cat. So this is just running cat 5 times, and it's sending data to cat 5 times. There's 2 overall approaches that you could have taken to solve this problem. One is to read input on standard input in your main process line by line, and then send it line by line to each of these sub-processes. I did it instead byte by byte, so one single byte at a time. If you sent it line by line, then you're going to see nice clean output that's like output, 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 one line at a time. If you're doing it like I am, where I'm doing it byte by byte instead of line by line, you might see kind of strange output like this, where each process gets a byte and then it can start doing something with it, and then it gets another byte and it can start doing something with it. So as I'm printing this stuff out, you can kind of see that the output is getting really like mixed together, and this is expected. This is expected output for the strategy that I selected for solving this problem. If you did this line by line, you'd see hello, 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 and then something, 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 all on their own line. But because I'm doing this, it's just 1 byte by 1 byte by 1 byte, read, send, read, send, read, send. It's kind of mixed together. It's all jumbled together here. So let's take a look at my code. I'm going to step through this, and then I'm going to give you a chance to ask some questions. I want to make sure that you're ready to start getting on the assignment, to start the assignment. So I want to give you a chance to ask some questions. If there are questions about this while I'm going through it, please don't hesitate to just raise your hand. If I'm not looking at you, throw something at me, something soft, throw something at me so that I am paying attention to you. Because if you have a question in the moment, other people have the same question in the moment, and it's going to be better for me to answer it in the moment than to try to come back to it and get ourselves back in that mindset. Okay, so I am going to leave this void ignore signal. You can see the pattern here. This is a signal handler. This is a signal handler. And it doesn't do anything. It receives the signal and it doesn't do anything. We'll ignore that for now, and we'll just keep moving down. I've got a function that I've defined here called split. For what we're thinking about, what we're familiar with, this is the same as Java split. Java takes a string, it splits on a token, and then it gives you back an array of strings. This takes a string and it splits on white space and it returns a 2-dimensional array of strings. I'm actually going to go straight down here for now just to show you what that looks like. The split function is actually as long as the rest of the solution is, but it's kind of like string manipulation stuff. So I'm using things like strdupe. I'm using things like strlen. I'm using functions like isSpace. I'm just going to tell you my approach, and I'm not really going to spend a lot of time looking at this. My approach was go through and count the number of spaces. So we've got input on each of those arguments. Count the number of spaces. The number of words that are in that is the number of spaces plus 1. And then I'm iterating through that using strtoke right here on line 119, and then just like copying those strings into a matrix of strings. Let's go back up to the main function. In my main function, what I'm doing is I'm creating an integer matrix for pipes. So it's a 2-dimensional array of pipes. It's a 2-dimensional array of integers. I need to have a pipe between my main process, 1 pipe per child process that I create. To have 1 pipe per child process, I've got to have a matrix, excuse me, a matrix of pipes. Oh, gosh. I have to have a matrix of pipes. Pipe IDX is something that I'm using later to keep track of which pipe I'm writing data to, reading from standard input, writing to a specific pipe, and then cmdargs is something that I'm just using for keeping what is returned by split. I'm going to ignore this comment. You can read it if you want for now. I'll come back to it in a second. It's related to the signal part, that signal handler that doesn't do anything. I'm doing dynamic allocation of pipes because I want to support any number of arguments here. I'm not saying at the beginning that there's going to be exactly 10 processes that you're going to launch. So I want to be able to support n, so as few as 1 or as many as thousands or whatever. All pipes here is size of int star times argc minus 1. So int star, this is the pointer part of your 2D matrix of integers. And then in here, on line 47, we're doing the other half of that. So on line 38, that's the long part. And then on line 47 is where we're doing the short part. This is the 2-entry part of the pipe. In my loop here, I'm looping over all of the things that have been passed to me. On line 43, I'm calling that split function. So it's just taking what was passed as argument whatever and then splitting it into an array. I'm dynamically allocating 2 integers for my pipe, and then I am creating a pipe between 2 processes, and then I call fork. A strategy that I've seen students do in other terms is like do all of the pipes and then start doing fork. And that's a good idea, but it leads to problems where you've got all of the pipes open in every copy of your process. And that means that you have to close all of the ends of the pipes that you're not using in all of the processes that you've copied them into. So at this point here, we've got one process. We haven't started anything yet. We call pipe. The operating system is creating that queue in the open file table or somewhere, but it's being referred to in the open file table. And then we're duplicating that process. So we're copying it. We're making a copy of it. We've got parents and child. In the child process is where the interesting stuff happens for now. In the parent process, the only thing that we're doing is closing the read end of the pipe. So pipe modifies the open file table in the parent process, in the main process. We fork, we duplicate it. And then we close the read end. When we go back up to the top of the loop again and we call pipe and then fork, the child process that gets created for the second one will already have had that part closed. We're duplicating the state that it is right now. The parent is never going to read from anything, so we just close the read ends of the pipes that we're creating as we're creating them. In the child branch is where the interesting stuff happens in this loop. We're not writing anything, so we close the right end of the pipe. Closing the right end of the pipe it's not essential. It's not essential. Your code might run if you don't close the right end. It might terminate if you don't close the right end. But I just close it anyway. Yeah, I just close it anyway to make sure that I'm tying stuff up that I don't need to have open. It's possible that a reader might block if there are right ends that are still open. And that is something that you'll observe, and what you're going to see is like the code will just stop and it will just get stuck and it's not going to proceed anywhere because somebody is trying to maybe write from this right end of the pipe and somebody's stuck trying to read from it. So closing our ends of the pipe makes sure that we don't get into that state. The next thing that we're doing here, replace standard input with the pipe. So the idea here is that we've got standard input in our main process. I'm slamming on the keyboard, I'm typing stuff in, and I want to send everything that I receive on my standard input to all of my children. They should all get the copy of the data that I have just read. The way that I want them to believe that they're getting input is that as though there's like monkeys slamming on the keyboard, typing exactly everything that I just typed in. And the way that I'm going to accomplish that is by changing their standard input. So I'm going to close their standard input, and I'm going to replace it with the read end of the pipe. Close and dupe2, these are modifying our open file table. They're changing our open file table. Close is removing an entry. Dupe2 is copying one entry and stuffing it into another entry. And after I call exec here on line 58, those changes still have effect. So I'm replacing myself. I'm asking, please run this program in my address space, but my open file table is still changed. So when I call dupe2 in my own code and then exec vp cat, as long as cat doesn't change its own standard input, it's just going to run believing that its standard input is the pipe. It's the read end of the pipe. I've got some extra code here. 59 and 60 are just like, I failed for some reason, exit. But on success, we're never going to get to these lines. We're never going to return back to our code. I'm going to pause here, take another drink so I'm not coughing up a lung, and make sure that we're okay with this.
So exactly the program that it runs, it gets the open file descriptors of the program.
Yes. So the question was, exec is the program that we are going to run, and it gets a copy of the open file descriptors that we've got. That's true? That's what you said? Yes.
But I thought like every program gets its own standard kind of file descriptors, right?
Yeah.
So like, if it has its own standard descriptor, how would it use the calling process?
Okay, so this is a great question. So the question is, I thought that all processes get their own copy of standard input, standard output, standard error file descriptors. How does that work? How does that work here? Every process gets its own copy of standard input, standard output, standard error. So when we start our process running, we've got standard input and we can start typing stuff in. There's standard output. We see stuff being printed to our screen. Those are the same standard input and standard output that the shell had. And the shell is a program that forked and exec'd our code. It's the same standard output and standard input. When I start this new shell here, on my right side here, I have a new shell that has a standard output and a standard input. On my left side here, this is Vim, right? But Vim is just a program that reads standard input and writes to standard output. It's writing to standard output in a really fancy way. Like it's making changes to things where we've got a cursor that moves around and we've got line numbers and we've got syntax highlighting. But this is just standard output. And it's the same standard output that this shell has. It's the same one. So when this shell forks and execs VI and passes octopipe.c, VI Vim is going to start writing to standard output, and it's the same one. So the operating system isn't like, it's not intervening here and saying, hey, here's a new standard output just for you. It's actually just the same one that that previous process had. So when I do things like make changes to standard output here on line 56 with dupe2, that still affects the child processes that I create. So when I fork and then when I exec, it still affects those child processes that get created. Okay. Okay. Yeah.
With exec VP, you're running basically octopipe again, right?
With line 58, this is run, I'm going to change this comment to say, please run main in something like cat. So cat is a program that has source code. It has its own main function, and I'm kind of implicitly asking for that main to start running.
Command arguments are the one that we pass to, like when we write like dot back dot.
Yes. So let me quit out of this again. This is going to be cat. This is going to be head -5, tail -2. This is going to be those things that we're passing to it.
When you refer to command arguments at 0, you're referring to head -5.
I'm referring to head, and then the array itself is head, and then -5, and then null. So there's this execvp is that null terminated array. Yeah. The second time I run through this loop, args at 0 is tail, and then args is tail -2, and then null. Yeah, yeah. Yeah.
So if program reads from center input, it'll always, like, can we always expect it to, it's always going to wait for input. Like, we don't, there's not going to be a time in which we get it.
That's right. Because you've already created this pipe here, by the time something like a program like cat or head starts reading on standard input, it's using the same system calls that we're using. So it's going to have like read in it, and it's going to be stdin file no, and it will block in that same way that I've described our programs as blocking. It just gets stuck there and it waits until there's actually data to be read. Yeah. Any other questions so far? Yeah.
You're basically taking the end and copying it to the standard input of the child process.
That's right.
But that type, does it automatically have the standard input of the parent?
It doesn't. It's just the pipe. And then what we're going to do after this, I'm going to scroll down, but I'm going to still hold for more questions. The part where we actually start writing to the pipe comes after this.
So we're going to have another call to start.
We're going to have to, we don't have to call dupe again, but we have to start writing to the process. Okay. Yeah.
Exactly. So let's say when you're off the pipe and then you give it one command, right? And then it waits for our input, we give it the input, then it just waits the output, right?
Yeah.
And then something that it was, but I don't understand how. It again waits for our next input and it would run the command again, right? But the first time the command was run, it was run using the execvp. But when the execvp is finished, it's terminated.
Yep.
It doesn't run again.
Yeah.
So, and when we give it the input second time, does it again create like a child process for the same command?
So a program like read, a program like cat, it's got a loop that's calling read. So in the same way when you were writing C programs in 2160, you'd say like while f gets something is not equal to EOF or 0 or something like that. There's a line like that, just like that in cat, except it's calling read in a loop. So it's just calling while read, and we're actually going to see that same code just down here in a second.
Oh.
But the loop that I'm showing you right now, it ends on line 67 here. So I haven't done any reading or writing yet. All of this is all that's happening right now is just these processes are starting. And they're all starting and they're all getting stuck on their own call to read on standard input because there's no data in the pipe yet for them to read. There's nothing in the queue for them to read yet. So they're all just blocked. Yeah. Okay. So I'm going to keep scrolling down. And here's my helpful comment. All the children are launched now. Everyone is running. All of these child processes are running and they're all blocked. They're all stuck on read right now. Here's the code where I actually start doing the reading and writing. Like I said, I'm doing this one single byte at a time, just one byte at a time. You might have done this with n bytes at a time, but I'm doing it just one single byte at a time. So I don't have an array, I just have a byte, a single byte, because I'm just doing it one byte at a time. This is only running in the parent process. None of the child processes they're never getting to this point because we've exec'd all of those child processes. So they're all running in cat and head and tail and stuff right now. They're all stuck, they're all blocked on their own read. My parent process on line 72 here starts reading my own standard input, which I have not changed. It's still my keyboard. It's still my keyboard. My open file table is still reading from my keyboard. I'm reading one single byte. And then for each child, I'm going to go through the pipe that corresponds to that child and write that one byte out to them. So I read a byte, I write a byte n times. I read a byte, I write a byte n times. I read a byte, I write a byte n times. Eventually what's going to happen is on my keyboard, on my system, I'm going to hit Control D, end of file. I'm not going to type anymore. And my read system call is going to return 0. There were no bytes read when this was flushed. So I exit that loop. And then once I exit the loop, I have to tell all of my children that there's no more input. The way that I communicate that to them, because after I've done write and then I do read, they're all stuck again on read. They're all blocked on read again. So I am going to exit this loop, and just after I exit this loop and start entering this for loop, all of those child processors are blocked on read. They're waiting. They're just holding it down because there might be more data coming. For me to go through here and then close all of those pipes, remove the write end from my open file table, tells the operating system that it can flush the reads for all of those other processes that are just sitting there waiting around on this pipe, waiting for inputs. They will all exit the read system call, and they're all going to get 0 bytes were read. It's the end of stream, so you can just proceed with exit, basically. And once we've closed all those pipes, then we should wait for all of the processes that we've launched. This wait system call, like I said before, this waits for a single child process to end. It waits for any child process to end, but just one at a time. So I have to call it that many times, the same number of times I called fork in my main process, to make sure that all of them have actually finished before I finish up here. I don't care in this program, I don't care about the order. Like, I don't care if it's the first process that I launched that ends first or the last one that ends first. It doesn't matter. I just want to know that all of them have ended by the time I'm finishing my code. If a process has already finished, which is possible, as soon as I call close, cat is going to start exiting because there's nothing left to read. Head is going to start exiting. Tail is going to start exiting because there's nothing left to read. So they might exit before I get here. If all of my child processes have exited by the time I start calling wait, then this doesn't block. It just immediately returns, and there's nothing to wait for. Yeah? Sorry, can you repeat the question? Yeah. Okay, so that's a good question. And this is where I'm going to go back up to the signal handling stuff. So at the beginning of my code here, I am registering this signal handler for sigpipe. Sigpipe is a signal that gets sent to a process that tries to write to a pipe that has been closed by the reader. There are no readers left on this pipe. If I try to write to something that doesn't have anybody on the other side, you know, I pick up my phone and I talk to it, but there's nobody there, I get a message back from the operating system that says there's nobody here. The default action for sigpipe is terminate. And it's terminate like gracefully, exit normally. And so after you hit enter on the 5th line of head, and then you try to start adding more to it, you try to write, and then you get sigpipe, and your process exits. And because it starts exiting, the operating system starts closing the right ends of pipes, and then tail will see, oh, my right end is closed, or the other side of this pipe is closed, so I'm going to start printing out my output too. My code, because I am handling this, and to be clear, just in case you're wondering, like, did I need to do this or not? You didn't need to do this. That's why I said, like, it's okay. It's okay if it does exit. My code here, so let me change directory to that. Summer, labs, lab 1, guide, octopipe. So my program here, when I do octopipe, I'm going to do head -2, so print out the first 2 lines, and tail -2. My program, because I am registering that signal handler and then just not doing anything, like just ignore it. There's nothing in this function. So if I write in something 1, something 2, these are the 2 lines from head right now. Something 3 doesn't print anything back because head is done. I'm going to keep trying to write to it in my code, but it's always going to give me sig pipe. But because I'm ignoring it, nothing happens. Something 4, something 5, and then I hit Control D, and then I get something 4 and 5 again, the last 2 lines of input. But just to be clear, you didn't have to do this. The reason why I said it might exit on its own, and that's okay, is because of what we have here. Yeah. Any other questions? Yeah.
And what's the parent? How was the parent closing all of the read ends? I think, or was it the right? Yeah. Why is it closing all the read ends?
So that's a good question. That's a really good question. So the question here is, this line here, 65, why am I closing all the read ends in me? Why am I closing all the read ends in me? It doesn't really matter. It doesn't really matter, because if somebody tries to write to that, which nobody ever will, nobody's ever going to try to write to the read end of this pipe other than me. Nobody's ever going to try to the only thing that's writing to this other end of this pipe is me. That's what I'm trying to say. That's the only thing that's writing to the other end of that pipe. If I comment that out, let's see what happens here. So I'm going to make that, and I'm going to run octopipe, and I'm going to run cat, 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 cat. Partly because I love it, and partly because it's simple. We should know what to expect to see as output from here. So if I run something, 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 like it's kind of the same output that we're expecting. If I hit Control D, it still ends normally. Part of me wanting to make sure that I'm closing ends of the pipe that I'm not using is just me internally knowing that if I don't close the correct ends of the pipes in all places, I can get into states where I just get stuck for unclear reasons. If I don't close this end of the pipe in my parent process, then all child processes have the read end of that pipe open. All child processes have the read end of that pipe open because I'm duplicating that PCB over and over and over again, and that open file table over and over and over again. So for me personally, it's just I want to make sure I'm cleaning up. I want to make sure that I'm not going to get myself into that state of processes are getting stuck waiting around for something to happen in a place where I don't understand why it's happening. Yeah.
So for this exact same reason, I thought like when we used to write,
Yeah.
it's a new entry, right? It's create standard input and it points to where the pipe was referring to.
So just a point of clarity. I'm going to let you finish, but I want to make a point of clarity. It's not creating anything new. This standard in file now already exists. There's already an entry in the table for that. It's just overwriting it. It's replacing it with something else that already exists. Yeah.
So we don't need to close that end of the pipe once we have used do. I thought because
If
we
you
have two entries that are pointing to the same end of the
Yeah, so if you do this, close all pipes, pipe IDX at 0. This is what you're asking, right? Yeah, so if we do this, that would be fine because there's 2 entries in the open file table that are pointing to that same queue. The close system call just removes an entry from the table. But with a pipe, we've got this kind of like extra thing that's sitting behind those entries. So at this point, after line 56 has ended, the state that we're in right now with the open file table is that all pipes at this pipes index and standard input file node, they both point at the same queue right now. So if I delete this one, if I close this one, it will just remove one of those entries, but the standard input one still refers to that pipe, to that same queue structure. Yeah. That's a good question. Thank you. Yeah.
Like the right end of the pipe from the previous child was still open for that second child, right? Like that's not an issue either.
That's not an issue. So the right end of the pipe for the second child. So as I'm going through this loop, so the first time I'm going through this loop, in the child process, I'm closing the right end. In the child process, I'm closing the right end. And in the parent process, I'm closing the read end. And so that leaves a right end open in the parent process. When I fork again, and then I go through this, I'm closing the right end. So that does kind of leave one open, I guess. Yeah, it leaves one open, but it's not a problem because there's nobody that's on the other side of the read end that pipe had, which is back to the parent process. Yeah.
The child process when it's run to that 59 line, then it gets caught in it, doesn't do anything after that. But when I have a program at the stage where I don't include the exact routine yet, then sometimes I see them go back to the loop again.
Yeah.
And fall. Like the child.
Yeah. So if I comment this out, if I don't exec VP, it's going to it will be like the parent creates a child process, and then the child creates a child, and then the child creates a child, and the child creates a child, and it just keeps going. That's not expected. We don't want that to happen. I mean, it's expected in the sense that if you don't replace your code with something else that doesn't fork, yeah. It's expected if you intentionally do that. If you put fork in a loop, it's going to cause like an explosion of processes to start showing up, yeah. Okay. We okay? Okay. All right. I'm going to switch back to my slides here. I hope that this was helpful in terms of getting ready to start working on assignment 1. We're going to talk about assignment 1. But I want to finish the IPC stuff first, in the sense that the IPC stuff that I'm going to talk about is like the last part of the assignment for assignment 1. The state that we are in right now, as of the end of this discussion, is that you can do everything in assignment 1 up to the very last part of it. You should be able to do everything there up until the very last part of it, which is using FIFOs, which is what we're going to start talking about right now. And even then, the FIFO discussion, there is some discussion of it in the video. There's some discussion of it in the textbook. So you should be able to get to that point. But let's talk a little bit about FIFOs. So FIFO, pipe, when we're creating pipes between process, and I'm using the word pipe, I'm using the word anonymous pipe, and I'm also using the word queue, but when I'm specifically talking about this idea that is the pipe system call, I'm going to use the word pipe and I'm going to use the word anonymous pipe. It requires that we have a parent-child relationship between two processes for communication. So in my octopipe code here, and when I run this with cat, 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 I've got pipes, anonymous pipes between octopipe and cat, and octopipe and cat, and octopipe and cat, and octopipe and cat, and octopipe and cat. This only works because I have forked and then execed those processes. There's no way for me to have a pipe between octopipe here and, for example, vim on this other side. There's no way for me to do that because they don't have a shared history. They don't have that shared open file table. This whole thing works because we're duplicating that open file table and we're referring to that same physical queue structure behind the scenes. Pipes with the pipe system call require this parent-child or sibling relationship between processes. We kind of didn't show this, but if you've got one parent and two children, the children communicate via a pipe because they share the same open file table as the parent process does. This is anonymous pipe. So anytime I say anonymous pipe, anytime I say pipe 2, anytime I say pipe, I'm usually referring to the same general idea of pipes between processes that are related to one another. Sometimes we want to be able to use pipes to communicate between processes that are not related to each other in a lineage, in an inherited way. Make FIFO is a function call. So section 2 of the manual page, just so I'm clear, when I put this notation like system call parenthesis number, I'm talking about the section of the manual pages that we're referring to. Section 2 is system calls. Section 3 is like function calls in the standard library. I'm going to move these chairs so I don't trip over them anymore. Make FIFO is a function call that creates a named pipe. A named pipe, another name for a named pipe is FIFO. And it looks like a file in a directory. It appears as a file in a directory. You type ls, you will be able to see a file that has this name. It behaves like a file in a directory in the same way that pipes do. We can call read on it, we can call write on it, we can call open on it, we can call close on it. It looks like a file in a directory, with the main big difference is that it doesn't take space on your disk. It doesn't consume any space on your disk. Let's take a look at some code. This is code that I posted up on the course webpage. It's there. You can take a look at it. I'm going to pop it up on my screen. The question that I've got for you to start thinking about is which one of these should be run first? I'm not going to give you a lot of time to answer this question, but I do want you to look at it and just think about it quickly. So I'm going to take 10 seconds and put them up on my screen. I'll give you 30 seconds to read the first bit of it and then make a decision about which one you think should be run first. So here's client. Here's server. I'm going to scroll down past all the includes here. We've got int main void at the top of each one of them. And you can assume that the server FIFO name is the same for both of them. I'm going to give you like 30 seconds to read these code samples and make a decision about which one you think should go first. So as I'm trying to tell you about Octopipe, my watch is going buzz, 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 buzz. This is too much information time. My daughter is sick. She's a little bit sick right now. She's got kind of an ear infection. And so she's at home right now. The school just called because my son has a stomach ache, and he thinks that he caught it from my daughter. So we told the secretary that my daughter has an ear infection. It's not infected, it's just inflamed. It's okay. She asked my son how his stomach felt at recess, and he said good because he was having fun. Based on these two, we've got clients on the left side, and we've got server on the right side. Based on the function calls that you see here and system calls that you see here, I'm going to ask you to put up, I'm going to have to do this backwards now. No, I'm going to go like this. Point which way you think should go first. Everybody, point which way you think should go first. Okay. Pointing was a good choice on my part because we're pointing the same way that I see. Whereas, like, I still have to do this. I don't know if you know this trick. This is L. This is left. If you put these fingers out like in front of you like this is left because it's an L. I do this, still have to do this all the time. It's really embarrassing. I have this advanced computer science degree, but I don't know left and right. Okay, so server, yes, we have to start the server first. Let's quickly step through what this code is doing. On the server side, we're creating the pipe. We're creating this named pipe. Make FIFO takes a file name and it takes some permissions. Files on our disk have permissions. We're going to talk about file systems later. But files that are on a disk have permissions attached to them. So we can read them, we can write them, we can execute them. And there's 3 different classifications of people or things that are in the system that can read, write, or execute. There's user, there's group, and then there's everybody. The make FIFO function call will create a file at that location. So temp fbristo pipe. After it creates the FIFO, this will immediately return. So make FIFO is not a blocking call. It just returns immediately. And then what happens here is we want to make a connection to the pipe. With pipe, with the system call pipe, when we called pipe, we got 2 file descriptors back, which is the same as what we get back from the open system call when we're reading files. We have to get a file descriptor for that FIFO by calling the open system call. It is a file. It's a file. As far as our code is concerned, it is a file. Open here, unlike in the previous places that we have used open blocks. So read blocks when there's no input on the queue or in the place where we're waiting for input. We're like, we have while read on standard input and nothing happens until we start typing stuff in. With the FIFO, open blocks. Only with the FIFO. When we open other files, open doesn't block because the whole file's there already. We can just start reading it. We can start doing stuff with it. But in this case, open blocks. And what we're waiting for is somebody to connect to the right end or to the other end of that pipe. I'm waiting for somebody to connect to the other end of the pipe. So open blocks here on line 30. And then I start running client.c. And I'm going to run these in separate windows. They are not related in any way other than being in the same directory on my file system, but they're not like parent-child relationship. I'm going to open the same file name. So my 2 processes have to know where the FIFO is. They have to know where that shared file is. But once I open here on the other end, so I'm opening read-only here, I open write-only here. Once I open the other end, then this open becomes unblocked. I return and I can continue going down here. The client code is reading standard input. It's using fgets. It's using the standard library functions for interacting with input. And what it does is basically just send stuff to the client, to the server, sorry. It writes stuff to the server. It's writing to the FIFO, and it's writing strlen bytes to the FIFO. And then we optionally have a command that we can send, which is exit. And exit is a way for us to tell the server we're going to send a specific byte sequence. And the byte sequence is, it's bell. If you take a look in the manual page at for ASCII, this is an ASCII table. I don't know how much you did this with Java in 1020, but like going back and forth between char and integer, this is a nice table. I don't know, ASCIItable.com was in my history for a long time until I found out that this is here, so now I just go and look at this. Bell is number 7 here. This is just a symbol that you can send, and bell just says, it used to actually be ring a bell, literally ring a bell, but now it's just a symbol that we can send. And the symbol on the server side says, I'm going to actually exit now. I'm going to finish up with this process, and I'm going to exit. So these are just reading on the server side, it's writing on the client side. And then we don't do anything in terms of closing the FIFO in the child side or in the client side. I'm going to try to stop using child here client. We don't close it. We just leave this as an unclosed file. Here we've got our loop that's reading stuff. We're testing to see if we get the bell. If we get the bell, we exit, and then we unlink this. Unlink is another system call or function call that you can make. Again, we'll talk about file systems later in the course. Unlink is different than close. Unlink removes the file from the directory in the structure that you've got in the file system, whereas close is modifying your open file table. We'll talk more about that later. Let's see what this does in action here. So I'm going to run this on my own system right now. I'm going to run client. I'm going to change my make file to include client and server. I'm going to run the server on this side. I'm going to stick to the way that I had it before. I'm going to run the server on this side. So in server right now, we are stuck on, and we are blocked on this. We're blocked on line 30. We're opening this file for reading, but we're blocked. We're not proceeding past this right now. This has created a file. I'm going to say ls-l temp fbristow pipe. It has created this file in my file system. I'm going to read a little bit of this to you. This P here is pipe. It means pipe. It could also say D for directory, or it could have dash for file. There's permissions here, R and W, and then this is execute. I am allowed to read this. I am allowed to write this. I am not allowed to execute this file. I can't run it like a program. The next 3 are for the group permissions, RWX, but group cannot do anything. The rest of the world cannot do anything. This is a file that's on my file system. And this tells us how many bytes are in that file. There are 0 bytes in this file. There will always be 0 bytes in this file because it is not actually a file. It's just a pipe that has been exposed on our file system so we can treat it like a file between processes. I'm going to run the client now. And I want you to kind of pay attention to what's happening to server. I'm going to hit enter on client and watch what happens on server specifically here. In client, I have opened it. So this is the other side of my pipe now. I've opened the FIFO for write access in the client. I was blocked opening the FIFO for read access in the server. But now that I've opened it for write access in the client, the server has unblocked after open and it has proceeded. And now it's waiting, it's blocked on read. It's trying to read the pipe. It's trying to read the FIFO, but it's blocked because there's nothing written to it yet. This file still has 0 bytes. There's nothing there. The client and the server can start interacting with each other. cat hello world. We're sending data from the client to the server through this pipe, and the pipe still has 0 bytes. The FIFO still has 0 bytes. The FIFO, like pipes, is just a queue in the background. There's still like send data over this queue. The client is enqueuing it. The server is dequeuing it. And we're communicating to each other using this file name as a well-known location. The other thing that this enables is that 3430, lectures, week 2, lecture 5, code, is that I can do things like start multiple clients to write to the same server. This is a different client. Hey, that's not me. That's fraud. No, it's me. We can have multiple clients writing to the same FIFO, and the server is able to receive and read that from both of those. I'm going to kill one of these servers by hitting Control-C, or so one of the clients by hitting Control-C. So I haven't registered one of those interrupt handlers. I've interrupted it. This client is still running, and this server is still running because there's still a writer for the reader. I'm going to do this, yes, and I'm going to write cat, and I'm going to pipe it to client. Okay, so yes is a program, it just writes a string out. It's an infinite loop that just writes the string that you pass to it. I'm piping standard output for yes to client. Client is reading standard input, and it's sending it to the server. I'm going to kill this client, and I'm going to do the same thing. Yes, dog. I'm going to print out dog in an infinite loop. I'm going to send it through client, and now they're both going to be writing to the server. The code that I've got here, and the code that you've got on your machine or that you've got on the website, is line by line. So it's reading one line, it's writing one line, and it's kind of doing this like that. Okay. The other thing that we can do, I've terminated both of my clients, so my server ends. The other thing that we can do with this is that because this server is just working with a file, it's just a file. It's just a file that's on my file system. Because it's just a file that's on my file system, I can use code and programs that don't know anything about pipes. So I can say things like, I'm going to cat client.c. So cat client.c is just going to print the contents of that file. I can do things like cat client.c. I'm going to redirect standard output, and then 2 greater than symbols means append to. I'm going to cat to temp fbristow pipe. This program doesn't know anything about pipes. Cat does not know anything about pipes. It knows how to read standard input. It knows how to write to standard output. It doesn't know anything about pipes. If I cat client.c, my server receives it because it's just writing to the pipe. It's writing to the FIFO. It doesn't know that it's a FIFO, but it's writing to it. Cat closes the file at the end, so we get this end of file, and then our server terminates. That's why the server is terminated here. Okay. So a FIFO it's a pipe, but it's a file. It's a queue, but it's a file, and we can have different processes interacting with that pipe because it's a file. They know how to open files, they know how to write to files, they know how to read from files, and because they can do all of that, they can interact with each other through this queue, through this pipe structure. Okay, I am going to, we did this, we did this, we did this. I'm not going to do this, but if you're bored, I invite you to do this with the friend. Do it with a friend, because this is an important part of this. Do it with a friend. I can do that really quickly. I'm going to say make FIFO. This is a command make FIFO and not the standard library function make FIFO. I'm going to make that FIFO. It's still just a file with no bytes. You can see that the permissions are different now because I haven't passed permissions to it with the make FIFO function. But I can do things like cat temp fbristow pipe, and I can cat hello.c to temp fbristow pipe. And now I have two cats talking to each other, but they don't know anything about pipes. They just know how to read from a file and write to a file. The last part here, I'm going to invite you to do this on your own. Have someone else write to your pipe. Try creating a FIFO. Connect to the same physical machine on Aviary. So if you're connected to Pelican with your FIFO, make sure your friend connects to Pelican. Change the permissions on the pipe. So I right now have this pipe. We've got user group world. User group world. World is these three here. You can change the permissions on a file using a program called chmod, C-H-M-O-D. C-H-M-O-D is change mode. Mode is the permissions for the file. And what we want to say is A, everyone, all things plus RWX, and then the name of the file that we want to change those permissions on. This gives everybody access to that. Everybody that's connected to the same physical machine can start to use that. If I do this now, if I list the contents of that file, it's got RWX, RWX, RWX. Everybody can do everything to this file. Try doing this on your own with a friend and read and write from the pipe across your connections. Okay. When the FIFO closes is when all of the writers have closed. So if there's many writers, as long as there's still one writer there, the file will stay open. The FIFO closes on the server side when there's no writers left. All right, okay, so I really want to get to this point, which is taking a look at assignment 1. I'm going to take a quick tour through this, a really quick tour through this. Yes, Rosen? How long does the temp file live for? It lives for as long as the machine is running. It will get cleared out when the machine reboots. So you might want to erase it, but it's an inert file. It's not really doing anything. Yeah, yes?
Writers and it closes, but you just make it like automatically.
So if you make it from the command line, then it's going to be still in that state of if you try to open it for read, it will block until there's a writer. So remember when I started the server up the first time, we call make FIFO and then we call open, but open doesn't return until there is a writer on that. It closed, so we exited the loop for the thing that was reading from the FIFO when there were no writers left on the other end of that FIFO. If you want to have that start up again, yeah, you'd have to make another FIFO.
It seems like it's only going on if you're sending
So if we want the client to send, if we want the server to send back to the client, there's kind of like a complicated setup here, which is that you need some structure. The client would have to say to the server, here is my pipe that you should write to. And then the server will say, OK, and start writing to this other pipe. So you have to have 2 pipes per pair of client and server if you want the server to send data back to the client. Yeah. And then it would have to be like uniquely named for the client itself. So the client tells the server, I want you to write to this file name. The server then writes to that file name, and that's what the client is reading on. Okay. All right. So we are going to get back to threads next class, tomorrow. But let's take a quick tour through assignment 1 in the next few minutes. The quick overall summary of assignment 1 is that you are going to be implementing a shell. Shell is in the context of like what we see here. I have fish running on my system, the friendly interactive shell, fish. On Aviary, you have TCSH. I don't know what it actually stands for. Sorry, I don't know what it stands for. Bash is the born again shell. Ash is, I don't know what. It's another kind of shell. There's just all sorts of shells. There's all sorts of different shells because everybody has an opinion and they all write their own shell. The difference between what you're going to be doing and what these do is that these are all interactive shells. They're sitting here waiting for you to start typing stuff in. You type stuff in and you press enter. Shells all have the ability to run a script, which is a non-interactive use. You give the shell a file name, and it will read the file from start to end, and it will run each line separately or run each command separately. You're going to be building a non-interactive shell for this assignment. Non-interactive shells will do things like reading files. They will do fork. They will do file descriptor replacement with dup2. They will do exec. They will do wait. They will use the same kinds of system calls that you have been using for your own process management code. I'm going to point at these. I'm not going to step through them individually, but these are firm requirements for submission. These are different from what's in the lab. They are more restrictive than what's in the lab. Please make sure that you're reading these before you start working too far on the assignment. The shell that you're writing is going to take commands, and it's going to run the commands within that single line. Here's an example of a command that your shell should be able to work with. This is a pipeline. It consists of 3 separate commands. This example consists of 3 separate commands. The first one is sort. Sort is a program that will take data line by line and sort it. The -r option says sort it randomly. So just like take whatever order, dump it back out in whatever order. This is a special syntax for something called process substitution. This will take this process, cat, user shared dict words, and this is going to write to what it believes is standard output. Sort is going to take a file name to replace this. So we just talked about something that's a file name. We just talked about files. So that's kind of what this idea is here. Cat and sort are going to communicate with each other through a FIFO. They're going to communicate to each other through a FIFO. Cat will be writing to the FIFO. Sort will be reading from the FIFO. When you do exec VP on sort here, it's going to have 3 arguments to it. Sort -r, and then the name of a file that it's going to start reading. Standard output from sort is going to be piped to this head program. You've seen head. That means that the stuff that gets printed on standard output from sort will be read from the standard input in the head program. We're going to redirect the output from head to a file that's named random.txt. So this says, this is the command. Standard output is redirected to this file name. Redirecting standard output is kind of the same idea as piping. You're going to use dupe2 to do this, change the file descriptors, change the open file table. But the difference between pipes and files for redirecting is you don't make a pipe to redirect to a file, you just open a file and then put that file descriptor in the open file table for output there. So your code is going to use pipe, make FIFO, fork, dupe2, wait, and the exec family of functions to do this. Here's an example of a script. Each of these lines will run to completion before the next line starts executing. In this script, the outputs depend on previous lines. Touch is a program that will create an empty file. So this one will create a file called touch.txt. ln is a program that creates a soft link. It's like a shortcut in a directory structure on the command line. This creates a file that's called words that head on the next line starts to read. This example script is like increasing in complexity. As you're building up your own structure to represent this, as you're writing your own code to do this, get the first line working, then get the next line working, then get the next line working, then get the next line working. Don't try to do the last line first, because that's basically everything up to that point. Try to get them working line by line. The structures that you want to start thinking about using for representing these commands, these pipelines, I would suggest, when I was thinking about this, when I did it, I used a linked list. I used a linked list. Linked lists. Linked lists are the best. They are everywhere. I used a linked list. Each one of these commands is a node. So cat proc self status, that is a node. Its next is grep nonvol. Grep nonvol is a node. These things are connected to each other in my linked list. That means that there's a pipe between them. So I need to open up a pipe to send data between them. There are some assumptions that you can make about this. I'm not going to read through those. You can read through those on your own. This is a shell. These are real commands. You can use a shell to verify your output. You can take this file, and actually I'm going to, I didn't do this, but I'm going to take this and I'm going to make a .sh file for you out of this file, out of this set of lines, so that you have a .sh file. If you use bash, B-A-S-H, bash, this will work. The default shell on Aviary, TCSH, doesn't support process substitution, so it doesn't have this idea of the FIFO as a named pipe. You have to use bash to do something like this, but I'll make that. Make shell script. Okay. Can you change the shell in Aviary? You can launch a shell. So if I SSH to Aviary, if I echo shell right now, it's TCSH, but I can just run bash. And then I'm in bash. Then I'm in bash. Still gives TCSH, but you're in bash. You're actually in bash. The way that you're being evaluated on this, there are some points for code quality. The programming standards document are posted to the course webpage under the assignment section, so you can find all of those coding standards there. The way that the implementation is assessed is that you are kind of like iteratively being assessed on this. So again, when I'm saying start at the top, make that work, and work your way down, it's because you're being assessed that way on this assignment. The command line parsing and redirection, this is basically, can you get the first line and the second line working, where you are running a command and redirecting output to a command. This one is piping. Can you get the piping working to go between processes? And then the last part is process substitution. So can you actually get the process substitution thing to work? Process substitution is files. It is not pipes. It's files. And I'll make sure that I've got something in the shell script to make sure that you can see exactly what that means. This part is a bonus part. And I've hidden the expectations here. I've hidden them. I've hidden the expectations here because it's a bonus. Make sure your shell works first. This part is really priming you for assignment 4. Like, let's try to do this when the stakes are very low. Assignment 3, the file system thing. Let's try to do this assignment. It's normally assignment 4. Sorry. It's priming you for assignment 3 to try to make sure that you have an idea of how to do this while the stakes are low before we get to like the big thing where we're doing the file system stuff. Don't do this unless you are confident that your shell works. Don't do this unless you're confident that your shell works. Yeah. Is it worth any marks? Yes, it is worth 5 points. So the first part is worth 25 points. This is worth 5 points. It's not nothing, but it's not maybe not worth your time if you're not confident that your shell works. Okay? It's a bonus, yes. Yes. Okay, so I'm going to get to threads next class. Quick summary. Lab 1, it's a lab. FIFOs are pipes, but for unrelated processes through the file system. Assignment 1 is an assignment, and I'll see you all tomorrow.